Oh, hi. Thanks for clicking play and letting me talk at you again. Let's talk a bit about gravity. Now, gravity is just the force of attraction between any two objects with mass. So, if you need to ask yourself, are these two objects attracted to each other, ask, does object 1 have mass? Does object 2 have mass? If you answered yes for both, then yes, they are attracted to each other. Aww. As you remember from Newton's third law, every action has an equal and opposite reaction. That means I pull up on the Earth at the exact same force that the Earth pulls down on me. And in orbit, it's not just one object circling another, they both orbit a common center of mass with each other. Now, if one object is way more massive than the other, it looks like one is sitting still while the other is circling around. But if they're a little bit more even in mass, you can look up binary star systems, then it's a lot more pronounced, this joint rotating, which is pretty cool. To find the force of gravity between any two objects, you'll just take g, which is a constant discovered by Cavendish and lovingly named Isaac Newton's universal gravitation constant. And that big G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So I'd take that G, multiply it by mass 1 times mass 2, all over r squared, where specifically r is the distance between the centers of the two objects. And even more specifically than that, it's the center of mass of the two objects. So as the Earth goes around the Sun, I would find the very center of the Sun's mass, the very center of the Earth's mass, find that distance, and that is that. Speaking of the Earth and the Sun, let's do a quick example of that. The distance from the Earth to the Sun is defined as one astronomical unit, which just happens to be 1.5 times 10 to the 11th meters. If the mass of the Sun is 2 times 10 to the 30th kilograms, and the mass of the Earth is 5.97 times 10 to the 24th kilograms, what is the magnitude of force between them? All right. Well, let me draw a little picture of what's going on here. And I did not fully succeed in filling in the Sun with color, just because I like being myself. But I'm given in the problem the distance between the center of the Sun to the center of the Earth. It's defined as 1.5 times 10 to the 11 meters. As the Earth goes around the Sun, orbits around it, this would be its orbital radius. Now technically it's more of an ellipse, but it's pretty close to a circle. So that's the distance between them. I know the mass of the Sun and I know the mass of the Earth. And I also know the value of the universal gravitational constant. So I have all I need to put together the equation for the force of gravity between these two objects. And again, the force of gravity is g times mass 1 times mass 2 divided by r squared. So just plugging in the values that I'm given, I get 6.67 times 10 to the negative 11th times 2 times 10 to the 30th times 5.97 times 10 to the 24th, all over 1.5 times 10 to the 11th squared. And punching that out into my trusty calculator, I end up with about 3.54 times 10 to the 22nd newtons. That's a lot of force. Except not so much. If you look at the Earth's mass and the Sun's mass, the acceleration would actually be pretty small for both of them. But that's the way it works. So here's what this means. This means the Earth feels that force and the Sun feels that force. Just following Newton's third law. The force that object 1 exerts on object 2 is the same as the force object 2 exerts on object 1. Doesn't matter if the objects are actually touching, pulling on each other, pushing on each other, whatever it may be. Or if it's just gravity, there's distance between them and it's the force of gravity. Doesn't matter. If there is a force exerted by one object on another, they feel the exact same thing. Which brings me to what's really going on when objects are orbiting each other. One of my favorite book series in the world is Douglas Adams' Hitchhiker's Guide to the Galaxy. If you've not read it, watching the movie doesn't count because it's way different. Go read it. That's a standing assignment for the entire year. The third book, the main character learns how to fly. The main trick is not thinking about it, and since the main character really doesn't think about a lot of things in general, it's the one thing he's really good at. But it says there is an art, or rather a knack, to flying. The knack lies in learning how to throw yourself at the ground and miss. Pick a nice day, the Hitchhiker's Guide to the Galaxy suggests, and try it. That's kind of what orbit is, though. Here's the way that Newton first figured out that the same force that causes an apple to fall from a tree onto his head is what keeps the moon circling up in the sky. Imagine you have a cannon, and it's sitting right on top of the Earth. It's a huge cannon, just right smack dab on the North Pole. And you fire the cannon at not too big of a velocity, and you see it kind of, the cannon's firing horizontally, and you see it kind of arc and then fall to the ground, like you're used to. With the only force after it leaves the cannon acting on it is gravity, so it only acts in the downward y direction. The x velocity is undisturbed, and you end up just seeing a parabolic arc as it falls and hits the ground. So you think, well, that was pretty neat. I'm going to try to launch a cannon even farther. So you fire with greater speed, and it arcs back to Earth at a greater distance. And in fact, the faster and faster you fire it, the farther and farther it travels. Eventually, you'll be able to fire it so far, it begins to curve around the side of the Earth before hitting. And eventually, beyond that, you'll fire it so fast that it travels and curves and arcs toward the ground, but doesn't actually get any closer, and then ends up hitting the back of the cannon. It traveled all the way around the world and didn't land because it had just that much horizontal velocity to keep it up. That's all that orbit is. It's something falling toward Earth and missing. And Isaac Newton, way back in the day, came up with this idea, which is just incredible to me. I would not have thought, as I watched the moon up in the sky, that it's the same force that brings an apple down. Now, I mentioned from Newton's cannon that you need a certain velocity. Anything lower than that, you'll start to spiral in and hit the Earth. Anything more than that, and it'll eventually just come out of the cannon, kind of slingshot around the Earth, and make its way away. Well, that's not exactly true. There is a range of velocities at which you would get some sort of elliptical orbit. But if you wanted a perfect circular orbit at a certain distance, here's how you'd find that out. In that case, the force of gravity between Earth and the object that you care about would be a centripetal force. And anytime something is designated as a centripetal force, anytime a force causes something else to move in a circle, it gets to wear a little badge that says equals mv squared over r, where m is the mass of the object moving in a circle. So it turns out it doesn't matter what the mass of your orbiting object is. If you know how far away it is from the center of Earth, and you know Earth's mass, and you know the value of g, you can solve for the velocity that is required to keep it going in a perfect circle. And we'll take a look at that again in a little bit. But until then, have a fantastic insert whatever time of day you're watching this video now. Bye.